Honorable scholars, I'm Meng from Shanghai Jiao Tong University. It's a great honor for me to attend ISGT-Asia 2022. The topic I'm going to share today is optimal strategy for customer Directrix node-based demand response considering comfort and preference of customers. My presentation consists of 5 parts. First of all, please allow me to begin with the first part, introduction. In September 2020, China clearly stated its 2030 carbon peaking and 2060 carbon neutrality goals. As the energy system with the highest carbon emissions, the power system is supposed to transform from the traditional high carbon form to a new power system which integrates high proportion renewable energy resources. However, due to the volatility and intermittence of RES, the flexible adjustment capacity of source side is overwhelmingly weakened, bringing critical power balance challenges to the power system. Meanwhile, with an increasing number of distributed energy resources, such as water heaters, air conditioning, and so on, the demand side involves great potential for flexible adjustment. Demand response is of great significance to effectively alleviate power balance burden of new power system by managing DRS to provide the increasing amount of flexibility. In recent years, a novel DR scheme based on customer Directrix node has been proposed, with advantages of avoiding overshoot and rebound in DR. CDL describes what shape of node curve is friendly to power system and is taken as the goal curve to guide customers' autonomous participation in DR. CDL is calculated through system-wide optimization for certain purposes, such as promoting RES integration. Therefore, customers with higher similarity between their power consumption curves and CDLs make greater contributions. However, the formulation of CDL lacks consideration of the underlying network, causing imprecise guidance to customers. What's more, the comfort of power consumption and subjective preference of customers are ignored in the implementation of CDL-based DR, which reduces effectiveness of DR. To bridge the gaps, our paper develops an optimal strategy for CDL-based DR considering comfort and preference of customers. Now let's focus on the framework of it. First, the node serving entity calculates CDLs of each node according to the network constraints and uncontrollable parts of power system, which cause power fluctuation. CDLs are broadcasted to corresponding customers to guide them to reshape node profiles. Then, typical weekly node profiles and regulating range are extracted to characterize the customer adjustability. Finally, HGMS automatically design an optimal power consumption strategy for customers based on the customer decision model. The compensation received by customers is related to their contributions. Next is the methodology part. We make the following assumption. The optimal economic power output of conventional units and maximal available RES output can be reached when calculating CDLs. The power output of conventional units is determined with the objective of minimizing total operation cost under the balance constraint of power summation over all time slots, as well as output and ramping constraints. The difference between each nodal CDL should be minimized to ensure the fairness of contribution evaluation. Hence, the CDL calculation model is established with the objective of minimizing the sum of Euclidean distances between each CDL under network and power balance for each time slot constraints. Then, the notion of typical weekly node is adopted to characterize the typical node profiles of customers, which improves typicality and representativeness of the profiles. In this part, the typical node on day Q of a week and the adjustment range of DR customers are obtained. As for the optimal decision model, a preference coefficient lambda ranging from 0 to 1 is leveraged to represent the preference of customers for comfort. The higher the coefficient, the higher the requirement for power consumption comfort. When lambda reaches 1, the customer quits DR and follows the typical consumption pattern with no contributions to the system regulation. A modified IEEE 9 bus system is applied to test the validity of the proposed model. Because of time limit, typical weekly load in first day of a week is taken as an example. The power consumption of DR customers under different lambda is presented. As shown, the CDLS of each customer are different from each other under network constraints. According to the network topology, Customer 1 belongs to node 5, where a wind turbine is located, and accordingly the profile of CDL is similar to that of the wind power output, so that more wind power can be integrated. Besides, with lambda increasing, the power consumption of customers deviates from their CDLS, while approaches their typical weekly load to increase their comfort of power consumption. It is worth noting that the power consumption of customers cannot coincide with their CDLS, even when lambda reaches 0 due to their limited adjustability. As for the DR performance at system level, the RES curtailment is reduced with the decrease of lambda. When lambda decreases to a lower level, for example 0.5, the RES curtailment decreases to 0, indicating that the RES is completely integrated. Therefore, further decrease of lambda is no longer needed, which causes more loss of customer comfort and is of no benefit to RES integration. Moreover, the RES curtailment decreases with the increase of DR percentage when lambda is large. In addition, it is clearly shown that the proposed DR scheme effectively reduces the peak-to-valley difference of net load. Besides, after DR is implemented, the RES output increases and becomes closer to its maximal output compared to that without DR. In the end, let's draw the conclusion. This paper proposes an optimal strategy for CDL-based DR considering comfort and preference of customers. First, CDLs are formulated under network constraints to precisely guide customers to participate in DR. Second, an optimal decision model is established considering both comfort and subjective preference of customers. Third, the simulation results demonstrate CDLs under network constraints vary from each other and unlock the flexibility of DR customers. Customers are enabled to reshape their load profiles to promote the integration of RES whilst maintaining their comfort of power consumption. The RES integration capacity of the system is considerably improved with the proposed DR scheme. That's all. Thanks for listening.